let's solve the following linear congruence. So let's solve 12x equal to 21 mod 39. So we are looking for integers x. We want to know what integers x are there such that 12 times x and 21 have the same remainder when divided by 39. Or in other words, when you multiply x by 12, you get a remainder of 21 when you divide by 39. And so there are a few questions we want to answer here. So first, does this congruence have any solutions at all, right? So that's a first question. Second, if it has solutions, how many solutions are there modulo 39, right? And third, what are those solutions? So this is slightly different from the examples where we could simply multiply by an inverse, because you can actually check that 12 is not going to have an inverse modulo 39. So there's no number that you multiply here and you get an inverse. The reason for that is that, as we'll see, the GCD of 12 and 39 is not going to be 1. And we saw that that's what we need so that there's an inverse. So how do we solve things like this in general? When are there solutions? When there are not? When there are solutions, how many, right? So let's see a general way of solving these type of problems. So here's the procedure for solving ax equal to b modulo n. So the first step is to compute the GCD between a and n. So this d over here, okay? So compute that GCD, and what will happen is, if d does not divide b to begin with, then there are going to be no solutions. So if you compute the GCD of a and n, and that doesn't divide b, you know there are no solutions. Now, when it does divide b, there will be solutions, and we're going to show how to find all of them. So if d divides b, what you do is you're going to divide all the numbers here, this a, b, and n, you will divide them by d, and you will get a new system, right? And the important thing here is that now a prime and n prime are going to be relatively prime. Their GCD will be 1. Why? Because if you look at a prime and n prime, so they share, so d was their GCD, so once you divide it by them, now the only divisor they will share is 1, because you removed all the divisors that they shared when you divided by d. And since now a prime here and n prime are co-prime, their GCD is 1, we saw in a previous lecture that then there will exist an inverse for a prime modulo n. And so what we'll do is we find that inverse, and we saw in a previous lecture that you can find it by the extended Euclidean algorithm. And with that, we are going to find one solution, which will be just the inverse of this times b. And that will give you one solution modulo n prime. But again, we are interested in the solutions modulo n, not n prime. And so every solution that works modulo n prime, so of course, if this is a solution modulo n prime, since n prime divides n, this will also be a solution, x0 will also be a solution mod n, but you can have other solutions of the form k times n prime. And so since the n prime is n divided by d, you will actually have exactly d solutions, and they will be given in this form here. So as a recap, to solve something like this, you find GCD between a and n. If that GCD does not divide b, you're done. There are no solutions. If it does divide b, you sort of divide this equation, all of it, by d. You will get an equation like this. This will be solvable by inverting a prime. That will give you one solution. And then all your solutions are going to be of the form that one solution plus k times n prime, where k will go from 0 to d here, to d minus 1. So you'll have d solutions. And so let's apply it to the example we wanted to solve. So let's do this. So once again, we want to solve 12x congruent to 21 mod 39. So the first part was compute the GCD between 12 and 39. And we saw how to do that through the Euclidean algorithm. So take the largest one, divide it by the smaller one. So this is going to be 12 times 3 plus 3. Now you take this number here and you divide it by this remainder here. Now you do 12 equal to 3 times 4 plus 0. And so now we got a remainder of 0. So it's going to be the previous remainder. And so what this means is that the GCD of 12 and 39 is equal to 3. Okay, so that was the first step. So once we've established that the GCD between 12 and 39 is equal to 3, we need to see whether the GCD here divides this number. So does 3 divide 21? So yes, 21, you can actually write it as equal to 3 times 7. And so this implies that 3 divides 21. And so there exists solutions. And we know already there's actually going to exist 3 solutions. So first, what do? We take this congruence and we divide everything here by 3. And so the 12 divided by 3 will be 4. And so 4x congruent to the 21 divided by 3 will be 7. And the 39 divided by 3 will be 13. So mod 13. And now, because we divided by 3, we know that 4 and 13 will actually be co-prime, so this will be invertible. But the point is, now we just need to solve this over here. Okay, so let's find the inverse of 4 modulo 13. So let's copy paste this here just so we have it. And let's put it up here. So now we want to solve this over here. So let's invert this. So find the inverse. So how can we find the inverse? We do the extended Euclidean algorithm. So we start with the largest one here. So 13 divided by 4 is going to be 4 times 3 plus 1. And the next one would be 4 divided by 1, which will be, the remainder will be 0. So we know that we just stop here. And so this implies that you can write the GCD between them 1 equal to 13 plus minus 3 times 4. And so this means that this minus 3 here is going to be the inverse of 4. So that means that 4 to the minus 1, the inverse of this is going to be the minus 3 modulo 13. And minus 3 modulo 13, so if you go the clock with the 13 numbers and you go minus 3 from the top, you'll get the number 10. So, or just doing 13 minus minus 3. So you'll get 10 mod 13. And so with that, we can just multiply by 10. You can also check if you multiply 4 by 10, you'll get 40. And 40, so let's write it here. So 40 is going to be equal to, so 40 divided by 13. So it's going to be equal to 13 times 3, right? So 13 times 3 is 39, and then plus 1. So you can see that indeed, if you multiply this equation here by 10 on the left, you're just going to get a 1. Okay. So if you multiply by 10, you'll get the 4 times 10 is going to be 0. So think of it like this. So 4x is going to be, so 10 times 4x is going to be congruent to 4 to the minus 1 times 4. Let's write it like this. X congruent to x. And so, and this part here, 10 times 4x is just going to be 10 times this. Congruent to 10 times 7. So this will be 70. And 70 mod 13. So if we do 70 divided by 13, we get, so let me write it here to the right. So 70 is going to be equal to 5 times 13 plus 5, right? Because 5 times 13 is 15, 1, 5, 6, yeah, 65 plus 5. So it's this. Okay, very good. So this would just be 5 mod 13. Okay, so this, so x equal, so let's write it like this. x0 congruent to 5 mod 13 is one of the solutions to this over here. But remember, we're not interested in, I mean, we are interested in solving this because we want to solve this. So we need to go back to our original. So now what happens is that the original modulus was 39, and we have found the simplified modulus 13. And since 13 divided by 3 is 39, we're going to have 3 solutions. So that means that our solutions are going to be, so our solutions will be of the form x congruent to 5 plus k times 13. So this x equal to 5, congruent to 5, was the solution for the 13. And then we add multiples of 13, mod 39. And we can add at most 3 of them, because when we pass, we're just going to go back the clock. So this will be for k equal to 0, 1, and 2. And so if we replace that, so we get, so let's write it like this. Thus, we have exactly 3 solutions modulo 39. And what are these solutions? So one solution is going to be congruent to 5. The other solution will be this, but with k equal to 1, so 5 plus 13, so congruent to 18. And the last solution will be congruent to 31, all of these mod 39. And of course, if you go and check, and one should, if you take, 5 times 12 and divide by 39, you'll get a remainder of 21. If you do 18 times 12 and divide by 39, you'll get a remainder of 21. And if you get, if you do 31 times 12 and divide by 39, you'll get a remainder of 21.